for the introduction, Yannick. I wouldn't say it's a solution to the POPLMAC challenge, or like the solution to the POPLMAC challenge. I would say it's like one approach to basically like how to tackle this this problem. And as Yannick said, I'm at Harvard University now, but like much of this work has been done already, or like started when we were both in Saarbrücken. Okay, so let's start. Yesterday, we saw that. So I should, of course, say that this has been work with many people from Saarbrücken. So there's Tobias Tabby, Stephen Schäfer, Jonas Kaiser, and Gerd Smolk have all worked on the Autosubst Autosubst project itself and have been in the papers. Okay, so yesterday we have seen that formalizing theorems about programming languages is fun, and in fact this has been done like for almost all of the proof assistants, and has often been used as like one of the like benchmarks, or like one of the first things that has been proven about proof assistants. So all these are examples of formalizations on the lambda about the lambda calculus in the most different proof assistants, in Lego, in the Rock proof assistant, Isabelle, and 12. But what we've also seen yesterday is that that sometimes formalizing things about binders requires some extra knowledge, and still is a topic which people talk about, for example, at these conferences. So there will be a leading question, and this has been the leading question for the Autosubst project. And the question is, how much does a user need to know about the formalization of binders to write such proofs about programming language in a general purpose proof assistant? So if you're simply on paper, most of these details are glossed over, of course. So this is one case where it's still done in quite some detail. This is from lectures on the Curry-Howard isomorphism, where a lambda calculus is introduced. So first, we have a definition of preterms. We have defined the notion of alpha equivalence, quotienting about these preterms. We define the actual terms as a quotient over these preterms. We have some definitions on terms. The authors say, like strictly speaking, we would have to demonstrate, like if you write like definitions on these terms, that they actually exist, like up to this alpha quotient. They explain like how they would do these proofs, and then afterwards they say, well, in the rest of these nodes, such considerations will be left implicit. And this is what's mostly done. Like either it's left implicit from the start, or like if it's like maybe like defined in the start, then it's left implicit at the end. And of course, in a proof assistant, we can't leave these things implicit. And as we've also seen yesterday. So instead of like just like having these formalizations, with the time there came a lot of like approaches how we can make explicit these things which are left implicit in a paper proof. So there were different approaches. For example, even like with the first approach, like of de Bruijn, who introduced that nameless syntax, their approaches based on like extensions of de Bruijn, for example, like making them scope safe. We have approaches based on horse, or like weak horse. We have even special proof assistants, like for example the Abella proof assistant we have seen yesterday in one of the talks. We have proof assistants like 12, which is based on horse, and like Beluga, which is on an extension of horse. And then we have papers which talk about like how to compare these different approaches and what are the different advantages and disadvantages of those. One of the very most famous of these like comparisons or benchmarks, Yannick has already mentioned in his introduction. This was the POPLMAC challenge, which basically asked to like how to formalize type safety for system F in part A, and then system F with patterns in and subtyping in part B. And one of the things which was marked as like one of the big challenges is that we have to talk about binding and about the treatment of alpha equivalent, and like how to make these things explicit in a proof assistant. So this Poppelmark challenge is now no more than 20 years old. Still yesterday, we still discussed like what the different approaches are and like why different approaches were chosen. So we saw yesterday, for example, an approach using de Bruijn. We saw an approach using like a special purpose proof assistant abeller. We saw one approach using names. So what is it? What makes it so hard to formalize binders? And what is the knowledge a user actually needs to know about the formalization of binders to write these proofs? So we talked about the different representations, and if you write such a different representation, we of course have to know like how to represent the syntax in such a system, and we have to know how to define, for example, substitutions or the lemmers in this. But this is not enough. We also have to know how to prove properties about the substitutions in this representation we are talking about. So what lemmers exactly hold or how they are formulated depend not only on the representation of syntax, but they also represent on the exact like implementation like of the syntax. So for example, whether we like do single point de Bruijn substitution or parallel pointed substitutions will give us like very different lemmers which we have to prove. Moreover, there's a lot of these structural lemmers. So this is a citation from Rosbeck and others when they like formalized properties about a module system, saying, well, there were around 550 lemmers, 400 were TDs infrastructure lemmers. They were quadratic in a number of variable cases. So there's a lot of lemmers, and it's important that we have these lemmers so that we can actually like prove the properties we care about. And even like the best automation doesn't help if we like later forget some of these infrastructure lemmers, which we require and can be found. So the question is like, which are the exact lemmers which we need, and like to ensure that we don't forget some of these lemmers which we require. And the third point is, even if we have all these lemma and all these infrastructure proven, there is a question how we apply them. So this is an example of using de Bruijn substitutions, which I think was yesterday mentioned to be very painful. So if I have, for example, a definition of de Bruijn and like, for example, want to prove something simple as like substitutivity of reduction, showing that S reduces to T implies like the same with the substitution on it. At some point in the case of beta reduction, I would like basically be stuck with proving something like this there, showing basically like that this composes in a good way. And to do so, I would require properties of substitution such as compositionality, distributivity, associativity, et cetera, et cetera. So the question is like, I don't only have to know like about like how the Bruijn substitutions are defined, but I also have to know basically like how the lemmers are used. Okay. So to summarize, we don't only have to think about like how to state the lemmers in the presentation, but we also have to know which lemmers on the substitution we should prove. We have to know how to prove them, and we have to know how to use them. And yeah, the Autosubst framework is basically a mix of two things to make this question easier. So I describe it always as like a mix of two things. So first is a choice of a binder representation and a choice of how to define substitution and which set of substitution lemma should hold, all implemented in to require minimum input from the user and done before on this, and like it basically assembles some of the parts to basically like have such a minimal representation. And second, it's a library, a tool, so that a user doesn't have to like prove all these lemmers and all this framework on its own, but this can be automatically generated. Again, requiring minimum input from the user. Okay. So how do we make this choice? Is based on a paper which comes from a completely different direction. It comes from calculi of explicit substitutions. So calculi of explicit substitutions were designed from another idea. So if you have like a definition, like a formalization about like if you have like the definition of a lambda calculus, there's often a big change between like how the theory is defined and how the actual implementation work, and this can lead to large blow-ups. And one core idea to make like the theory and the implementation basically closer was to make substitutions part of the object language. So this is this work by Abadi, Cardelli, Korean, and Levy. And from this, basically, like a long part into research followed. Okay, so we see here how this would look like. We have the definition of terms and we have the definition of substitutions. Substitutions are not something which are part of like the meta language, but they're really like syntactically part, like we have syntactically this definition of substitution. And this definition substitution, they basically like restrict itself to some kind of primitives we will talk about in some slides. Okay, and then we have some equational theory about it, talking about like what the equational theory on this like calculi of explicit substitution, talking about this entire substitution act, but also, for example, having something as meta reduction in there. Okay. What does all of this have to do with a good binder representation? Well, when these calculi of explicit substitutions were designed, it was taken great care that, for example, the rewriting system, which we see there, is defined to have good properties such as convergence and termination. I say termination because termination with beta doesn't hold, but termination without the beta rule basically holds. And we can use these if we're talking about the meta theory of programming language. Okay. More specifically, there is a paper from 2015 from Schäfer, Smolka, and Tebbe. This was really the start of the Autosubst project, which showed that the de Bruijn substitution algebra in Coq is sound and complete for this calculi of explicit substitution, and that it is decidable following from previous work on the calculi of explicit substitutions. Okay. What do I mean by this being sound and complete? Well, let's talk first about soundness. Soundness basically leads us back to one of the first approaches to binders. This is an extract from the 1970 paper by de Bruijn, where he used his automath proof assistant to prove the Church-Rosser theorem. And you can already see some of the things people say today about de Bruijn. So it's useful for a computer, and for a computer program, it's usual. Sorry. It's useful for reasoning it. It doesn't satisfy this criteria of being easy to write and read for the human reader, which, if you're just talking about meta theory, is not the main concern. So what is the idea? The idea is that we basically reduce a problem of alpha equivalence by saying that basically making this choice canonical. So alpha equivalence will be just definitional equality by saying that like binders are represented by references and basically like induce a scope change. We can, of course, represent this in a proof assistant. For example, this would be the definition in the RUC proof assistant. We have an inductive type term. We have a variable constructor, which is like this natural number, which will be like this reference later on. We have application, we have lambda. And if we define this lambda here, we have the scope change implicitly. Okay. So for example, in this case here, in this example term, like this is set under another binder would basically have to be increased by 1. Okay. And this is what we have there. Okay. Second, also de Bruijn already defined the notion of parallel substitutions, and we can do the same in the proof assistance and define substitutions on there. So we want to define instantiation. Instantiation will basically like take a term, take a substitution, and return a term with the substitution applied. Important, the notion of substitutions we have here is the notion of a parallel substitution. So we basically replace all the variables at once. So we had a function from nut to terms. And examples of these substitutions we would have would be exactly the primitives we would have from the sigma calculus we have seen before. There is some notion of an identity substitution, which basically like leaves all the variables intact. We can lift all the variables by once. This would be this shifting. And then we have this cons operation, which replaces the first variable by some s, and then by continues with like substituting the rest with a primer sigma. Okay, and then we can define the instantiation with substitution by basically like going over the term homomorphically. In the case of a binder, like in this case of this lambda there, we would have to shift the variables we have in there. So the first variable still would like stay with the 0, and everything else would basically be shifted by one. Okay, so those who have implemented this in a proof resistant or like or for example in ROC or Lean know that this definition has some small one small subtlety, mostly that here in this definition here we again require substitution. So as easy as this is not structurally recursive, and we actually have to define instantiation with renamings first and then can go on to instantiation with substitutions. Okay. And this has been done by de Bruijn. This has been done also by other people, for example, by Adams in the ROC proof resistant. In fact, we could have a version which doesn't require this renaming and substitution shift. This is, for example, topic of this paper, substitution without copy and paste by Altenkirch and others. But it requires us basically to have some notion of like lexical well, how to basically like go to the recursion lexically. Okay. And then in a third step, to make this sound for the sigma calculus, we would have to prove these lemmas correct we have seen for the sigma calculus. Okay. And most of these lemmas would also be familiar to those who have like proven something about substitution. So of course, like we basically like have to satisfy the equation we defined for substitution, instantiation of substitution before. We would have some lemmas basically talking about the interaction of the different primitives we have talked about before, but we would also have some kind of some laws that it basically like that substitution with identity returns the original term, or that basically we have compositionality of substitutions. And all of this would, for example, like if you define this with de Bruijn, this would be like known lemmas, for example, known as monad laws. Okay, so soundness, no problem. But the real interesting thing is that this is also complete. What do I mean by complete? I mean that these laws, which I have defined with the sigma calculus, they actually suffice to talk like they basically like are able to like prove all they suffice to prove all the equations we could have on terms and substitutions we want to have. I also said previously that the sigma calculus has been designed carefully such that it has good properties. So we have actually also a convergent rewriting system. And all of this together means that if I have two terms S and T with substitutions on them, I can actually decide them via the above reading right system, right? So what this means is if I have two terms and I want to know whether they are equal up to substitutions, I can normalize them, compare them syntactically, and look whether they're exactly the same or not. And all of this can be implemented via rewriting tactic, which in Autosubst is called simple. So let me show a very concrete example. So let's say we want, for example, prove type safety for the lambda calculus. We have done this definition of reduction. We have the case of beta reduction, which can be defined via the primitives of the sigma calculus. This is defined here. That S reduces to T implies like substitutivity with sigma. If we now do the proof, we would get stuck at this point here, where we basically like have to prove this equation on substitutions. So remind that this was a lemma which we had proven before, and this would be the loss which we would have before. Sample tactic, we basically like normalize both of the sides, and as they are like syntactically equal, we can simply use a reflexivity tactic, of course, to show that this to close this case. Okay. So from where we have been before, if you're asking like which how to like which lemmers we have to prove and how we prove them and how we use them, we have actually like solved most of these using this completeness rewriting system. We still have to know like how to state lemmers in this presentation and with the Brown. But the question like which lemmers on substitution, like substitution alone, is basically we have to we have to show the lemmers which have been there for the sigma calculus, and we can use them, prove them using techniques which have been previously introduced, and we can use them by simply using a rewriting tactic. Okay. More importantly, this way of reasoning scales to not only talk about the lambda calculus, but also to more extensive syntax. So for example, if you want to support like functor structures, so for example, I have a list of terms and I want to do substitution over them, I can, for the substitution, simply use the functor map for this. For reasoning, I can use identity and composition of functors in the identity and composition laws respectively, and I can prove the same set of lemmers I've previously seen for the sigma calculus. Or if we want to talk about many-sorted syntax and vector substitutions, if we want to talk about many-sorted syntax, for example, in a call-by-value system F, where we have both type variables and we have value variables, we can do a parallelization of the substitution we have, replace at the same time type variables and value variables, get a value back, and then we can lift the reasoning principles to basically have an extension of the reasoning laws we saw before for the sigma calculus. Okay. This also extends, for example, to variadic syntax. There we can't work with just like the primitives we have seen before for the sigma calculus, but we actually have to lift them to talk about like n-ary lifting and like n-ary shifting and n-ary like extension. But again, we can adapt the reasoning principles and we can adapt the definition of instantiation. This also works for more safe versions of syntax. So for example, there's well-scoped syntax for those who haven't seen this. The idea is basically that the terms which we have are indexed by the upper bound of free variables. So for example, we have here a term, and we have like indexed it by a natural number at. And then if we are going to the variable constructor, we don't take something out of like the natural numbers, but we bound it by this finite type of at most n variables. And in the case of a lambda, we basically like allow it to have like one more variable in it. Okay. And the advantage of this being that if we define rules, we have the advantage that one of the big disadvantages of the Brown, which is like we could write some lemmers which later don't hold because we have like forgotten some shift and later run into problems. Isn't a problem anymore because we would basically get a type error if we define a definition, for example, where we would forget the shift operator. Okay. So I said that this scales, and I've said that we basically like know which lemmers we to prove, how to use them, and how I prove them. Well, I lied a little bit. Well, yes, in principle we know how to prove them. But in reality, like this will be a lot of lemmers which we have. Let me show me an example. So this is a quotation from the Poppermac challenges talking about the Brown. And it says, another popular concrete representation is the Brown's nameless representation. It's easy to understand, supports the full range of induction principles needed to reason over terms. But the notational clutter is manageable for toy examples, but it becomes quite a heavy burden even for fairly small languages. This is, like I said, the example which was used in the Poppermac challenge and for this language to which it should be extended. So why is this? Well, you can have a definition of, for example, like types, and we can have a definition of terms and values. So this isn't any like size up which we have before. If we define substitution, we already have to define more for this because we have to remember that if we are working with structural recursion, we have to define it first for renaming and then substitution. And then also we have to ensure that that the lifting, which you have seen, like the scope change, which you have seen previously for abstraction, is basically implemented for every exchange of binders, which we have, for example, for types over values or values over types. Okay. And then we come to the proofs, and proofs look something like that. That is an extract of like basically like proving the calculus of explicit substitutions. And of course, we know in principle which ones to do, but like doing this will actually be technical. And moreover, like if we forget like one or two of the lemmas which we have seen previously in the list of things, the reasoning is not anymore complete, and we can spend some time basically like looking why what we have doesn't like reduce to a normal form, meaning that we actually have to know like what exactly about, like we have to know more details about the exact definitions and about the exact lemmas. Okay, so one of the main culprits why this is so long is that we have to define it both, for example, for renaming instantiation. So, for example, to prove this compositionality law, we would alone like need 8 lemmas until we get to the part that we actually can show this law for substitutions. Okay, but luckily, Autosubst doesn't just like have this choice of binder representation, but it also gives us a library tool to automate this corresponding boilerplate, including the automation technique, so that really minimum input is used from the user. So there are different approaches on how we could find this binder boilerplate here. So here are some examples. So for example, yesterday we have seen that, for example, we could use a general, like a special purpose proof assistant, like for example, a Beller. There are also other approaches, for example, which define some kind of definition of the terms and then proves properties about this abstract representation of the terms. In Autosubst, we follow the approach of code generation, meaning that we basically generate the code of the lemmas and the substitutions which we want to have. I would say this is arguably like less elegant than, for example, having an algebraic approach. We did it mostly for practical reasons, meaning that we can really reason directly on the inductive terms. We directly see the definition of substitutions, and we will see when I talk about like some case studies on this, why this is relevant. Okay. So what we have is Autosubst get some kind of specification lemmas talking about like the syntax we want to like generate, and it will give us some output file giving us expressions, the instantiation, and all the reasoning principles. Okay. You might see that in the specification which I've given here for the lambda calculus, we don't talk about variables. And which variables would be required to define substitution would actually be automatically determined from the Autosubst compiler. So, for example, in the case of a system f call by value, it would automatically infer that the minimal set of renamings and substitutions we require is we require a definition of like type substitution in the case of types, and we require both like type and value substitutions and terms and values. Okay, and then from this abstract definition, it would basically generate the proof terms, and it would generate like the lemma statements from which would give us the correct set of lemmas. Okay, and in general, it does this for this kind of like this amount of like this different like syntactic constructs. So we can do so for scoped syntax. We can do so for polyadic binders. So, for example, like having both a term, a type, and a value variable bound at the same time. We can do so for first class renamings. We can have like external sorts and sort constructors, many sorted syntax, mutual inductive syntax, variadic syntax, and also modular syntax. Okay. There have been different adaptations and versions of the Autosubst library. So the first one was implemented basically using Rock's internal but just like talking about, for example, lambda calculus, this would work perfectly. So there was a reimplementation which basically like worked externally and then generated the proof terms to also inspect. There have been also like an OCaml version and a partially working meta-rock version developed by a student at Saarland University. And also there have been some recent re-implementations or like substitution inspired by Autosubst, for example, as a backend in the T-Leaves framework by people at UPenn, or as a lean emulation by Marmaduke and others, who then like implement the simple tactic basically as like the rewriting a primitive in lean. Okay. Also this summer there has been work. So I said in the beginning, like when we talked about the calculi of explicit substitution, I said like we don't care so much about like how efficient things are, but actually like efficiency has been sometimes a problem in the rewriting, in particular if you use Citroid rewriting in Rock. So there has been some work on how to basically like on how to have like user reflection to implement these rules of the sigma calculus directly by Theo Winterhalter and the student. Okay. We have also used Autosubst beyond binder boilerplate because in the end, like what we care about is we care about basically reducing the boilerplate and reducing like basically like enabling like reusability for proof assistance. So to give some details. So last week, I was at the EuroProofNet workshop on proof libraries, and it talks about all these libraries for proofs and like how we can use them. But the problem is that it's really hard to have this reusability if we are talking about inductive types and proofs, and how we can basically like reuse some of the statements here, for example, lambda calculus, for more extensive statements. Let me make this precise. So if you, for example, start to prove properties about a lambda calculus, and you give recursive definitions on the terms, you prove things by induction on the terms, and then you also, for example, do predicates and proofs over the terms. And if you want to extend this calculus, for example, by Boolean expressions, even if these like sub-statements and sub-lemmers would be basically the same, as we would have for the simple lambda calculus, we can't simply like import them or like from a library as we would do for other library definitions if, for example, we talk about formalized mathematics. So, for example, a type safety proof, as we have talked about before, like for binders, would have the exact same reasoning whether we talk about a lambda calculus or if we talk about a lambda calculus extended by Boolean expressions. But we can't just port this, and this is known as, or like known from functional programming as the expression problem. So there have been various approaches to do so. So there have been like some plugins in Rock which like started doing this. And really what we want to do is we want to avoid this kind of like copy and paste. And also there have been some approaches to encode this modularity via encoding of functors. But the problem is once we go via an encoding, we have the problem that we have some indirectness and we can't use directly the approaches which we like the tactics and the reasoning which we would like in a proof assistant. So for example, like direct access to the inductive types or like direct definition of the function and the computation. Okay. So one approach which we can do is we can extend the boilerplate generation of Autosubst to do so, to have an approach to modular syntax for the Rock proof assistant. How this is done is basically inspired by data types a la carte, using some slight modifications, basically talking about like basically generalizing about over the functor which we later want to have and then later instantiating it. So in data types a la carte, we would define this type of expressions and would parameterize it by this expression type we later want to talk about, and then define this general inductive type where we basically where we basically like do this application of this functor. And of course, this definition which we would have wouldn't be accepted by a proof assistant, but general direct instantiations would actually like satisfy the termination checker. Okay. And we have done so using an extension of Autosubst to generate some of the boilerplate and also some assembling via the meter rock tactic. Okay. So how far does this scale? This actually scales up to proofs of type safety and strong normalization. And line of code wise, we really have something which would have a comparably like small overhead compared to a non-modular development. And so achieved by this mix of library and meter programming. And of course, this isn't perfect because we are because like so far this has been mostly trying basically how this works in general, but we would require, for example, like better tactics to seamlessly change between these modular and non-modular development. Yeah, and there has been some recent developments about family polymorphism by people at Stanford on how to maybe have a modular development. Okay. So I've talked about some of the extensions of Autosubst. So let us look at some of the examples and case studies, what we can do with this. So of course, I already said like one of the core benchmark is the Popple Mark challenge. And so Autosubst has been evaluated using both part A and part B of this Popple Mark challenge. So here we see the example of like part A, and the good news is that this really gives us some very concise proofs compared to other solutions. I should say, to be fair, that we still require to know how to state the lemmas. Good for us, there's a lot of literature on like how to reason with substitutions with de Bruijn and like what are the right lemmas we would have to do. So while still needing the lemma, still needing the lemma statements, the proofs itself would follow exactly like what we would expect, and there's nothing unusual about them. So one of them, for example, being the candidates for substitution paper, which defines like how we define like the context renaming in context morphism lemmas in the case of de Bruijn. It has been also used for part B. For part B, there are far less solutions than for part A of this Popple Mark challenge. Most of them, all of them here actually using de Bruijn. There's one solution in 12, and I heard that we heard today maybe about a solution using the nominal approach in the second talk of the session.
Part A. Can you recall what is part A and part B again?
Yes. So part A is basically like type safety for system F. Together with some notion of like basically like having transitivity of the subtyping thing, and then part B is talking about also pattern matching. So it meets the definition of variadic binders. Okay. We have also used it on a proof of strong randomization and compared it to an ACTA library and like it's a special purpose proof assistant Beluga. And the really good news is that though we are working in a general purpose proof assistant, the line of code is actually similar to what we would have in the special purpose proof assistant there. So this is a quote from this paper. Like we really have like the main challenges, they are really different, like similar in size and scale, whether we use this, for example, the de Bruijn approach, or whether we use, in this case, Beluga. And of course, this depends on like what these approaches support. Okay. There have been also external projects using Autosubst. So, for example, it has been used to prove several statements about programming languages. For example, there is a proof about that type checking is undecidable in system F subtyping. There is a recent development about the meter theory of Martin-Löf type theory. There are proofs about like CPS translations for the pure lambda calculus. And it has been further used in other projects. Oh, I still wanted to say that some of the projects which we have here they have also like led some of the extensions which we have seen for Autosubst. So for example, this paper by Forster, Kirsten, and Weir, they really cared about because their properties which they are very careful about the axioms. They care about like whether functional extensionality should hold or not. So a first version of Autosubst used, for example, functional extensionality, but like following these considerations, like actually we can prove all the lemmas we have there using equivalence and then not requiring functional extensionality. Some of these approaches also like extended the files which we have for Autosubst by custom principles they needed to reason in their case. So for example, this mechanization on the meta theory of Martin-Löf type theory required the notion of well-typed renamings, which could be extended because actually the code which we have can be accessed and we can actually like change it if we need it. Okay. So what are some of the limits and challenges? So all the reasoning and all the completeness I've talked about basically holds only if we talk about assumption-free lemmas. So this means that if you're talking about lemmas such, for example, as anti-renaming, where we have like to make like inversion principles over something with syntax, like this decidability wouldn't help us that much anymore. So this is an example of the Popper-Mark reloaded challenge, talking about the strong normalization the lemmas, and this is the kind of lemma. So in this case, I would need some inversions on this statement with a renaming. Interesting enough, this wasn't just like approach and a problem with the approach which we have chosen and with Autosubst, but it has also been a problem for example, for the Beluga proof assistant, which is like specifically built for this case. So this seems to be a general problem. And also we would want to have some support in the case that we are talking about like substitutions appearing in assumptions we have in our proof assistant, requiring some notion of matching. And then recently there has been quite some support, for example, to talk about substitutivity, for example, if you're talking about syntax traversals, and if you're talking about inductive types with substitution on them. Okay. And then there's also been quite some work in the last years on like how to have support for more eccentric bindings. There has been, of course, also work as on the nominal package, but more recently there has been quite some papers about, for example, support for substructural systems, both using the Brown application. So this is a paper basically extending an approach by Guillaume Allaire and others, or and this is approach using a Beluga, or for example about infinitary syntax, which I think we will hear in the next talk. Okay. So to come back to the initial question, how much does a user need to know about the formalization of binders? We have seen that we can build a system both based on the Brown, which actually requires the user to know about like how to state lemma statements, but doesn't require them, for example, to prove any lemmas about prove the general like lemmas about substitution, but would actually like automate it for themselves, working for a wide range of syntax. And yes, with this, I come to the end of my talk. Thank you for listening. I'm looking forward to any questions.